Lesson 4.4 covers an introduction to the simplex method. In the previous linear programming problems from the graphing method, each inequality had at most two unknown variables. We had an x and a y, and these problems were no problem to graph. If we have more than one unknown variable, could we use the graphing approach to solve the problem? So for example, if we had x plus y plus z is less than or equal to 2, could we graph that? We could still graph with 3 variables, but you would have to know how to graph in 3 dimensions. And even then, the shading for that can be quite complicated to do by hand. The simplex method is a method that can be used to solve some linear programming problems that involve more than 2 variables. There are several conditions that need to be met in order to use the simplex method. So we're going to look at the standard form for a maximum problem. As you go through this lesson and the next couple of lessons, just be warned, the details are very important. Don't skim through this material and think that the little details don't matter. They really do on these. So this is a lecture you might want to even watch twice just to catch all the small details. Let's first consider the linear programming problems in which the objective function is to be maximized. You can use the simplex method when solving problems where the objective function has to be minimized, but for this class we're only going to look at the maximized problems. So to solve these maximum problems, they must be in standard form. In other words, they must meet the following 2 conditions. You've got to know these conditions. The first condition is all variables are non-negative. The second condition is all other constraints are written as a linear expression that is less than or equal to a positive number or a positive constraint. So when you are trying to determine if a maximum problem is in standard form, be sure to consider both of these conditions. And just to make these conditions make a little more sense, let's look at an example. So for our first example, I want to maximize p is equal to 3x sub 1 plus 4x sub 2. Now if you notice, in these problems we're not using x's and y's. With the linear programming problems, all of our variables will be x's and we'll use subscripts. Our constraints are 3x sub 1 plus x sub 2 is less than or equal to 6, and x sub 1 plus 4x sub 2 is less than or equal to 74. And then instead of having x and y greater than or equal to 0, we have x sub 1 and x sub 2 greater than or equal to 0. So let's look at our 2 conditions. If you remember the first condition, there are no negative variables. And we know this is true because if you look at your constraints, the last 2 constraints, both of our variables are set greater than or equal to 0. So that tells us that both of our x's are going to be positive or 0. They can't be negative. Since we're told those variables are greater than or equal to 0, our first condition is met. Now our second condition is each constraint less than or equal to a positive number. And that is also met. Each inequality that we have in the first 2 inequalities for our constraints is less than or equal to a positive number. Because both conditions are met, this problem is in standard form. So let's look at the second example. I want to maximize p equals 2x sub 1 plus 2x sub 2 plus 3x sub 3. And the constraints are x sub 1 minus x sub 2 plus x sub 3 is less than or equal to 6. X sub 1 is less than or equal to 4. And then I have x sub 1, x sub 2, and x sub 3 all greater than or equal to 0. So for the first condition, look at your variables. I have 3 x's, x sub 1, x sub 2, and x sub 3. My final constraints tell me that all 3 of those variables are greater than or equal to 0, so my first condition is met. There are no negative variables because each variable is set greater than or equal to 0. Next, you look at the other constraints. Look at the other two inequalities. I have to have those less than or equal to a positive number. Well, each inequality is less than or equal to a positive number, so the second condition is also met. Because of this, this problem is in standard form. Now let's look at some examples that are not in standard form and specifically focus on why they're not in standard form. So in the first example, I want to maximize 2x sub 1 plus x sub 2 plus 4x sub 3. And my constraints given are 2x sub 1 plus x sub 2 plus x sub 3 is less than or equal to 10. And then I'm also told x sub 2 is greater than or equal to 0. Well, our first condition is that all the variables must be non-negative. Well, if you look, I have an x sub 1, an x sub 2, and an x sub 3. But I'm only told that x sub 2 is greater than or equal to 0. I'm not told or I'm not guaranteed that x sub 1 and x sub 3 are greater than or equal to 0. Since those two constraints are missing, my first condition fails. There could be a negative variable because the problem did not tell me x sub 1 and x sub 3 are greater than or equal to 0. So our conclusion here is this is not in standard form. In the next example, I want to maximize p equals 2x sub 1 plus x sub 2 plus 4x sub 3. My first constraint is 2x sub 1 plus x sub 2 plus x sub 3 is less than or equal to negative 1. And then I have each of my variables greater than or equal to 0. So our first condition is met. There are no negative variables because each variable is set greater than or equal to 0. Now let's look at our second condition. Our second condition fails this time because the first inequality is less than or equal to a negative number. So since condition 2 fails, this problem is not in standard form. Let's look at our next example. I want to maximize p equals 3x sub 1 plus x sub 2. And my constraints are x sub 1 plus 3x sub 2 is less than or equal to 4. And 2x sub 1 minus x sub 2 is greater than or equal to 1. And then I'm given that x sub 1 and x sub 2 are greater than or equal to 0. So the first condition is that my variables have to be non-negative. And this is true because I'm told both x sub 1 and x sub 2 are greater than or equal to 0. My second condition is that all other constraints, besides these last two listed, all other constraints have to be less than or equal to a positive number. This condition fails because my second constraint is greater than or equal to a positive number. Since the second condition failed, this problem is not in standard form. So let's look at the final example. I want to maximize p equals 3x sub 1 minus 4x sub 2 plus 8x sub 3. And my constraints are x sub 1 minus 4x sub 2 plus x sub 3 is greater than or equal to negative 12. X sub 1 plus x sub 2 plus x sub 3 is less than or equal to 16. And then each of my variables, x sub 1, x sub 2, and x sub 3 are greater than or equal to 0. The first condition I check for is make sure my variables are non-negative. And I know this is true because I'm told each variable is greater than or equal to 0. So condition 1 is met. The second thing I look for is my constraints. All the other constraints have to be less than or equal to a positive number. This is true for the second constraint, but not for the first one. I have greater than or equal to a negative number. So This condition fails because the first constraint is not less than a positive number. Because of this, this problem in its current form is not in standard form. Now I want to focus on this example for just a minute. It's a little bit different because even though it wasn't given to me in standard form, I can rewrite it and put it in standard form. Let's look at that first constraint, and I want to multiply both sides of that inequality by -1. When I multiply both sides of an inequality by a negative number, you've got to remember to switch your inequality sign. This is just a rule from your previous algebra classes. So if I multiply each side by -1, I get negative x sub 1 plus 4x sub 2 minus x sub 3. Then my inequality sign reverses, and -1 times -12 is a positive 12. Since multiplying by a negative number reversed the direction of the inequality symbol, and also multiplying the -1 by the -12 made it a positive 12, the constraint now passes condition 2, because that constraint is now less than or equal to a positive number. So as I mentioned, even though the original problem was not in standard form, it could be rewritten and made to fit standard form. So let's look at some more examples and determine if they can be put in standard form. The reason the first example was not in standard form is because the first condition failed. I was not given that x sub 1 and x sub 3 were greater than or equal to 0. So I want to know, can I rewrite this in standard form? This one I cannot, because I cannot add a constraint. If I wasn't told that these were greater than or equal to 0, I can't add them into the problem. So this problem is not in standard form, and it cannot be put in standard form. In the next example, the second condition failed because the first inequality was less than or equal to a negative number. So I want to know, can I rewrite that so that it's less than or equal to a positive number? Multiplying by -1, like we did with the last example, would also change the inequality symbol to greater than or equal to. I could multiply this -1 by a -1 to make it positive, but when I do that, it's also going to reverse the direction of my inequality symbol, and it would cause it to be greater than or equal to the 1, and I can't have a greater than or equal to. It's got to be less than or equal to. So this problem cannot be put in standard form. And let's look at the last example. This example was not in standard form because the second condition failed. My second inequality is greater than or equal to a number. Now I can change a greater than or equal to sign to a less than or equal to if I multiply each sides by a -1. So multiplying each side by negative would change this inequality sign to a less than or equal to, but it would also make this 1 become negative. So I would have less than or equal to a negative number, and that still fails condition 2. So this problem cannot be put in standard form. So to sum this up, the only time a problem can be changed to standard form is when one of the constraints is greater than or equal to a negative number, because multiplying by -1 changes the inequality to a less than, and it changes that negative number to a positive. And as I said, we always change this to standard form by multiplying the entire constraint by -1. The next topic we need to look at are slack variables. Before we get into solving maximization problems or max problems, we need to look at another concept. So let's look at inequalities for a minute. If I have 2 is less than or equal to 5, is there a number that I can add to 2 that would make that an equation? So is 2 plus some number equal to 5? And this is true. I could add a 3 to the 2 in order to make it equal 5. Well, we call this number that we add to an inequality to change it to an equation a slack variable. So a slack variable will balance the sides of an inequality so that it becomes an equality or an equation. So the slack variable is basically the number we add to one side of an inequality to make that inequality become an equation. Well, if you remember, in the Gauss-Jordan elimination method, we were working with equations. The simplex method is going to be very similar to the Gauss-Jordan elimination method in that we must be working with equations. In order to solve a max problem using the simplex method, we've got to introduce slack variables in order to make the inequalities become equations. So in general, our slack variables are denoted with the letter S. The variables in our problem that we're solving for, we use X's. The slack variables, we use S's. And we can always assume that the slack variables are non-negative. So let's consider this inequality. I have x sub 1 plus x sub 2 is less than or equal to 10. So the x sub 1 plus the x sub 2, that's my smaller sum. That side is smaller than or less than the 10. So in order to change this to an equation, I would need to add a number to that smaller side to make the two sides equal. So we could make this an equation by introducing a slack variable. We always put the slack variable on the lesser side or the smaller side. And since x sub 1 plus x sub 2 is less than the 10, we're going to add the slack variable to that side. So we end up with x sub 1 plus x sub 2 plus s sub 1 equals 10. So the s sub 1 is that slack variable that we added. I don't know what number I need to add, so it's unknown to me. I'm just going to call it an s. And since I need to make that side bigger, I know I'm going to add a positive number. I wouldn't add a negative number. Adding a negative would make it smaller. So I know that slack variable I'm adding is going to be greater than or equal to 0. So we assume that the slack variable is positive. If it was negative, it would make the left-hand side even smaller, as I mentioned. So the left-hand side would have been smaller than 10. And just a quick example to show this, if I have 4 is less than or equal to 10, if I add a negative number, let's say I add a negative 1, which is the same as subtracting 1, that would give me 3 is less than or equal to 10. So that doesn't make that an equation. It doesn't make that left-hand side bigger. It made it smaller. So by making the slack variable positive, we're increasing the value of the left-hand side. So that's why we can always assume these slack variables are going to be positive. If we had another inequality to change to an equation, we would use the s sub 2. Basically, I can't let my second slack variable be an s sub 1 because I don't know that I'm adding the same number to each equation. You just assume they're going to be different. And since these are different, each slack variable needs a different subscript. If I needed a third slack variable, I would let it be s sub 3. All your slack variables are going to use the variable s, and you increase the subscript by 1 each time. So let's look at this max problem. I want to maximize p equals 3x sub 1 plus 4x sub 2. And then my constraints are 2x sub 1 plus 4x sub 2 is less than or equal to 120. 2x sub 1 plus 2x sub 2 is less than or equal to 80. And then I'm told each of my variables, x sub 1 and x sub 2, are greater than or equal to 0. So first, just to review, I want to determine if this is in standard form. The first thing I look for is I have two variables, x1 and x2, and I'm told that both of those are greater than or equal to 0. So condition 1 is met. Then you look at your other constraints. Both of my other constraints are less than or equal to a positive number, so condition 2 is met. Now I change this to a system of three equations. And note that the objective function is already an equation, so it doesn't need any slack variables. It just becomes our third equation. For the first two equations, I'm going to take my two constraints, introduce the slack variables, and make those equations. So I start off with 2x sub 1 plus 4x sub 2 is less than or equal to 120. If I introduce my slack variable, I get 2x sub 1 plus 4x sub 2 plus s sub 1 equals 120. Then take your second inequality. Since this is a second equation, I'm going to use a different slack variable. I'm going to use s sub 2. So it's going to become 2x sub 1 plus 2x sub 2 plus s sub 2 equals 80. And as we mentioned before, both of our slack variables are greater than or equal to 0. Now our third equation is the objective function p equals 3x sub 1 plus 4x sub 2. Since the other equations have a number on the right-hand side, we're always going to write the objective function in this form also. We're going to subtract the x's from each side so that they are moved over to the side with the p. So if I move the 3x sub 1 and the 4x sub 2 over to the side with the p, they both become negative. So this gives me p minus 3x sub 1 minus 4x sub 2, and you've got to have your equals 0. So now we have the following system. Our constraints were the two equations that we got after we introduced the slack variables. The objective function is rewritten so that it's always set equal to 0. And then our variable restrictions, every variable, the x's and the slack variable s's, are all greater than or equal to 0. Once we have our equations, we're going to transfer those to a simplex table. So let's look at the basic setup for a simplex table. We're always going to start with what we call our basic variables, and we'll talk more about those a little bit later. Then we're going to have a matrix. That matrix is going to contain several column labels that consist of our x's and our s's, our equation variables and our slack variables. And then there's going to be an equal to bar, and then we have just what we call our right hand side, which is what all of our equations equal to. So the column labels and the right hand side are going to be contained within the matrix. The basic variables are going to be in front of the matrix. Where the equal to sign is in your equations, you're going to have your equal to bar, just like with the Gauss-Jordan method. Then the simplex table has one additional bar. It's always going to have a horizontal line that separates off the objective function. You'll always write your objective function last, and it'll be separated from the constraints with this horizontal bar. So let's look at our basic variables first. You always determine your basic variables because they have a coefficient of 1 and zeros everywhere else in their column. Now the basic variables may change each time we perform the elementary row operations. So every time you do a row operation on your table, you've got to check to see if your basic variables have changed. And then the last basic variable, the last element, will always be a p. That will never change. For our column labels, we're always going to have the p first, and that comes from our objective function. We're going to follow it with all the x's, and then we follow the x's with the s's, the slack variables. And as I mentioned before, the right-hand side is simply the number on the right-hand side of the equal signs. And then other notes, as I mentioned before, there's always a vertical bar to the left of the right-hand side, and there's always a horizontal bar above the objective function row, or it's often called the P row. So let's set up the simplex table for this problem that we had. I always begin by deciding what labels need to go above my simplex table. And it's easier to insert the numbers if the labels are already there. So we always begin with a BV, and that's in front of the matrix. And then inside the matrix, the first basic variable is always going to be a P. Then we're going to list the X's and then the S's, and it always ends with the right-hand side. So for this example, I'm going to start with my basic variables, and then I'm going to start my matrix. The first column label inside it is going to be a P. Since I have an x sub 1 and an x sub 2 as my variables, I need a column for x sub 1 and x sub 2. I had to introduce two slack variables, so I need a column for the s sub 1 and a column for the s sub 2. Then after my final slack variable, I put the right-hand side. The right-hand side and the slack variables are separated by a vertical bar, and then I finish out or I close my matrix after the right-hand side. Now let's take our first constraint, the 2x sub 1 plus 4x sub 2 plus s sub 1 equals 120. This constraint does not have a p, so you put a 0 in the p column. The coefficient for x sub 1 is a 2. The coefficient for x sub 2 is a 4. The coefficient for s sub 1, my first slack variable, is a 1. This equation does not have an s sub 2, so I put a 0. And it equaled 120, so I put a 120 under my right-hand side. Now let's look at the second constraint. It does not have a p, so put a 0 in your p column. The x sub 1 had a coefficient of 2. The x sub 2 had a coefficient of 2. This equation did not have an s sub 1, so I put in a 0. The coefficient for s sub 2 was a 1, and it equaled 80. Now I draw my horizontal bar, and I enter in my objective function. Well, it has a p, and its coefficient is a 1. The coefficient for x sub 1 is a -3. The coefficient for x sub 2 is a -4. This was already an equation, so it didn't have any slack variables. So the s sub 1 and the s sub 2 were both 0. And this equaled 0, so for my right-hand side, I put a 0. Now I've got to determine my basic variables. So let's look at row 1. I want to scan across that first row until I find a 1. And I've got a 1 under s sub 1. Then I check if this is a 1, are all the other elements in that column zeros, and they are. So then you go up to your column label. Since that's s sub 1, my first basic variable is going to be s sub 1. Now look in your second row and find the 1. This time I have a 1 under S sub 2. It's a 1 and every other element is a 0. So since that's my S sub 2 column, my second basic variable is going to be S sub 2. Then look in your final row. I have a 1 underneath my P. It's a 1 and every other element in that column is a 0. So my last basic variable is my P. And as we mentioned before, the last basic variable will always be a P and it will not change. Let's look at the steps to setting up the initial simplex table. Step 1 is make sure the problem is in standard form. Step 2, we convert all the inequalities to equations by introducing slack variables. Step 3, we decide what labels we'll need for the initial table. And then finally in step 4, we draw the initial simplex table and be sure to include all the labels. So we're going to look at the first 2 examples that were already in standard form and then the example that we were able to put in standard form and create the initial simplex table for each of these. So our first example was already in standard form, so that's step 1. We've already determined that it was in standard form. Then in step 2, I'm first going to take my constraints and turn those into equations. So if I take that first inequality and I'm going to add an S1 to the left-hand side, and that gives me a 3x sub 1 plus x sub 2 plus s sub 1, my first slack variable, and that changes the inequality to an equal to 6. Then for my second constraint, I add an s sub 2 because this is a different slack variable. So I have x sub 1 plus 4x sub 2 plus s sub 2 equals 74. And then take your objective function and we're going to move the x terms over to the side with the p. When I do that, they change signs. So I have p minus 3x sub 1 minus 4x sub 2, and that now equals 0. So step 3, we need the following labels. So our table is always going to begin with the basic variable. And then we have a p. And then we have 2 x's, x sub 1, x sub 2. And then we have 2 s's, the 2 slack variables, s sub 1 and s sub 2. And then we're always going to end with RHS for our right-hand side. Now let's look at the initial table. I'm always going to start by listing my basic variables in front of the matrix. Then within the matrix, you're going to list your P column, followed by your X's, followed by the S's, and then you have your equal to bar, and then you'll have your right-hand side. So if I look at my first equation, it did not have a P, so the P is 0. The x sub 1 coefficient was a 3. The x sub 2 coefficient was a 1. It had an S1 and its coefficient was a 1. It did not have an S2, so I put a 0 there, and it equaled 6. In the second equation, I did not have a P, so that's a 0. The coefficient for x1 was a 1. The coefficient for x sub 2 was a 4. I did not have an s sub 1, so I put a 0 there. And my s sub 2 had a coefficient of a 1, and it equaled 74. Then my equation from the objective function, it had a P with a coefficient of 1. The x sub 1 coefficient was negative 3. The x sub 2 coefficient was negative 4. It didn't have either slack variable, so put zeros in for each of those, and it equaled 0. Now I want to fill in my basic variables. So look for columns with a single 1 and zeros everywhere else. The first one will always be my first column. The 1 is in the last row, and that's the column for my P, so my last basic variable is always P. Then if I look, my next column with zeros and ones is under S1. The 1 is in row 1, so my first basic variable is S1. Then under S2, I have zeros and ones as well. The 1 is in row 2, so my second basic variable is S2. So this is the initial simplex table for the first example. Now let's look at the next example. We've already determined that this one was in standard form. So now let's begin with our constraints. With my first constraint, I'm going to add an S1, and I get x sub 1 minus x sub 2 plus x sub 3 plus the s sub 1 I added, and that makes that equal 6. My second constraint, I add an s sub 2, so I get x sub 1 plus s sub 2, and that makes that equal 4. Then go to your objective function. I'm going to move all the x's over to the side with the p, and when I do this, they each change signs. So I have p minus 2x sub 1 minus 2x sub 2 minus 3x sub 3, and that now equals 0. So when I'm determining which labels I need, look back at your equations. I always begin with a basic variable, and there will always be a p from the objective function. Then I had 3 x's, I had 2 slack variables, and I always end with my right-hand side. So now let's look at the initial table. Always begin with your basic variables outside. Inside the matrix, you're going to start with your p, then your x's, then your s's, and then your equal to bar, and finally end with the right-hand side. So for my first constraint, it did not have a p, so that was 0. X sub 1 had a coefficient of 1. X sub 2 had a coefficient of -1. X sub 3 had a coefficient of 1. I had one s sub 1. I did not have an s sub 2, and that equaled 6. In my second equation, I did not have a p, so that was 0. X sub 1 had a coefficient of 1. I didn't have an x sub 2, x sub 3, or an s sub 1, so they were all 0. And my s sub 2 was a 1, and that equaled 4. Then for my objective function, the coefficient of p was 1. The coefficients of x sub 1 and x sub 2 were both -2. Then I had -3x sub 3. This did not have any slack variables, and it equaled 0. Now my initial basic variables, the last basic variable should be your p. If you look in your p column, the 1 is in row 3, the third row. Your first 2 basic variables should always be the first 2 slack variables. And if I check, under S1, the 1 is in row 1, so that means my first basic variable is S1. Under S2, the 1 is in row 2, so my second basic variable is S2. So this is the initial simplex table for example 2. Now let's look at the third example. For step 1, this problem was not originally in standard form, but we were able to put it in standard form. I took my first constraint and we multiplied each side by -1. This gave us a constraint that was less than or equal to a positive number, which is what I always want. I need my constraints to be less than or equal to a non-negative number. So use that modified constraint for your first equation. When I do that, I get -x sub 1 plus 4x sub 2 minus x sub 3 plus the slack variable that I have to introduce, and that causes that to equal a 12. Then my second constraint, I had x sub 1 plus x sub 2 plus x sub 3. Then I add in my second slack variable, and that causes that to equal a 16. Now for my objective function, move your variables to the other side with the p, and they change signs. So I have p minus 3x sub 1 plus 4x sub 2 minus 8x sub 3 equals 0. Next, we determine which labels we need. Well, I always start with my basic variable, and then I have a p. This time I have 3 x's, 2 slack variables, and then I'm going to end with my right-hand side. So if we set up our initial table, fill in your column labels. Equation 1, the coefficients were 0, -1, +4, -1, 1, 0, and that equaled 12. Equation 2, my coefficients were 0, 1, 1, 1, 0, 1, and that equaled 16. Then for my objective function, my coefficient for p was a 1. The coefficient for the x's were -3, 4, and -8. It never has slack variables, and it always equals 0. And as we saw in the two previous examples, our initial basic variables are S1, S2, and the P. Now I've mentioned how to find the basic variables. Let's just fill that in on the notes. Each time we perform row operations, the basic variables, which I'll always label with a BV, usually change. The way you identify them, look for the columns that resemble a column from an identity matrix. You're looking for a single 1, and all other entries in that column need to be zeros. The variables above this column become the basic variable. And just recall the following about the basic variables. They have a coefficient of 1 and zeros everywhere else in the column, which we just mentioned. They're going to change as we perform the elementary row operations. And the last basic variable will always be p, and it will not change. Well, now to label the other basic variables, you look for the 1 in the columns. Wherever the 1 is, that tells you what row that column label is a basic variable for. So let's look at an example of a simplex table, and let's label the basic variables for this one. Well, first, since the P, the X1, and the S2 have columns that mirror an identity matrix, these are going to be our basic variables. We know from the definition of the basic variable that the last element will be p, so you can automatically fill that in. And if I look at my first column, I have the 1 and the zeros. The 1 is in row 3, so that p is going to go in row 3. Now we have to determine the basic variables for the first 2 rows. Take it one column at a time. You find the 1, and that will determine the row where the basic variable will be. So if I look at the column under x sub 1, okay, I know that x sub 1 needs to be a basic variable. Since the 1 under x sub 1 is in row 1, x sub 1 will be my first basic variable. Now we look at s sub 2 because it has the 0 and the 1s below it. So we know s sub 2 will be a basic variable. Since the 1 is in row 2, then the s sub 2 is going to be the second basic variable. So as we said, we always look for the zeros and the 1s. Now let's take a look at this final table. My basic variables were x sub 1, s sub 2, and p. So my table is going to give me answers or solutions for those. If you notice, the x sub 2 and the s sub 1 are not basic variables. Any variables that are not basic variables will always equal 0. Now, to find the value of our basic variables, we look to the right-hand side. If I take x sub 1 and go all the way to the right-hand side, that tells me the value of x sub 1. So x sub 1 is going to equal a 12. S sub 2 will equal an 8, and P will equal a 10. Well, if you remember, I only want the answers for my P and my X's. So I didn't need the slack variable. I didn't need to know that it equaled an 8. I only used those slack variables to change my inequalities to equations. So we're just going to focus on the X's and the P. So our final answers are x sub 1 was 12, x sub 2 was not a basic variable, so it equals 0, and P equals 10. Well, let's look at one more final table. We're going to take this table and label our basic variables and then label the solutions. Well, look for your columns with zeros and ones. My columns with 0 and 1s are under the P, the x sub 2, and the s sub 2. So this means that x sub 1 and s sub 1 are not basic variables, so they both equal 0. My last basic variable is always going to be the P. And now go to your columns. Since the 1 under the x sub 2 is in row 2, the x sub 2 goes in row 2 of our basic variable column. So it's my second basic variable. Since the 1 under the s sub 2 is in row 1, s sub 2 goes in row 1 of the basic variable column. So it becomes my first basic variable. Now to list my answers, s sub 2 equals 10, x sub 2 equals 40, and P equals 180. Just look at the right-hand side column in the same row as that basic variable. Now we don't care what the s's are, we just want the x's and the p's. And we don't have x sub 1 listed, so I do need to list it with my answers. So the x sub 1 was the 0, and the s sub 1 is also a 0. So the final answers that we want are the x's and the p's. So x sub 1 is 0, x sub 2 is 40, and the P equals 180. When you're listing your final answers, you don't even have to list what the s's are. We'll never want those. When you're asked for final answers, we always just want the x's and the P.